Okay, so last lecture of this course today. So today I want to show you how we can apply organometallic reactions in catalysis to produce useful products. However, before we go to that, there's still one migratory insertion that I wanted to show you. It is called the carbene migratory insertion. And in this case, our neutral ligand is just a carbene. So we have a carbon rhenium double bond. So in this case, the unsaturated ligand would be an organometallic fragment, basically. But this organometallic fragment can also undergo a migratory insertion. So one can insert formally the CH2 group into this rhenium carbon bond here with the methyl group as an anionic ligand. So that produces then an alkyl ligand, which in this case is not stable because it has a beta hydrogen. You have learned in the last class that when an alkyl group has a beta hydrogen, it can undergo beta hydrogen elimination to form an alkene. So now let's, however, really go to applications of organometallic compounds in catalysis. So one application is catalysis for hydrogenation reactions, and one important organometallic compound that acts as catalysts to catalyze these hydrogenation reactions is so-called Wilkinson's catalyst, which is this rhodium complex here. So we see here that rhodium is bonded to 3-triphenylphosphine units and the chloro group. Again, this catalyst is actually pre-catalyst. It's in chemical equilibrium with the catalyst, which has a lower coordination number, and this catalyst is just formed by statistical loss of one of the 3 bulky triphenylphosphine ligands. So this species, just by the way, is also in chemical equilibrium with its dimer. So this reactive species with a coordination number of 3 can also dimerize to form this species. But again, this species is actually not the actual catalyst. Only this rhodium complex with a coordination number 3 is. So what this species can do is that it can pick up hydrogen. It can add hydrogen in a reaction, which you should now be able to easily identify, which would be N. So it's an oxidative addition. So we add the hydrogen, we make here a dihydride, and that happens under the oxidation of the rhodium because the 2 hydridoligands formed are anionic. So the oxidation number of the rhodium must increase. So we also increase the coordination number, in this case from 3 to 5. So this is a trigonal bipyramidal complex, and statistically this complex here can add a free triphenylphosphine ligand to make an octahedral complex. So this octahedral complex is in equilibrium with this trigonal bipyramidal complex, whereby the octahedral complex is not catalytically active. Only this species here with the coordination number 5 can undergo further reactions. So now in the next step, this species here can add an alkene, as shown here. Okay, and that alkene simply adds to the complex, just increasing the coordination number. Okay, from 5 to 6, so the olefin binds side on to the rhodium. So now, in the next step, we transform this complex with the alkene bonded side on to this complex, and again you should be able to identify what reaction this is. So this is a even unsaturated ligand here next to a anionic ligand, a hydride ligand, so we can do a migratory insertion. Okay, so that migratory insertion then creates a new anionic ligand, which is now this alkyl group. Okay, and then this complex here can undergo another reaction to form then the alkane. And then we have actually completed our hydrogenation reaction. We have transformed an alkene to an alkane. And that reaction step, of course, would also have a name, which would be reductive elimination. All right. So we eliminate basically this hydride group and this alkyl group to make it alkyne in reductive elimination, and then our catalyst is actually being reformed. Okay, so this is one application of an organometallic compound as a catalyst, in this case to catalyze a hydrogenation reaction. So yeah, here are just the additional the steps which I actually just have explained. The last step is a reductive elimination. Okay, so another important process, which is industrially very important, is Ziegler-Natta polymerization. So we make all kinds of polymers, for instance, polyethylene or polypropylene, using that kind of reaction. There are two kinds of polymerization catalysts, heterogeneous catalysts and homogeneous catalysts. The mechanism of the heterogeneous catalysis is not so well understood just because it cannot be studied very easily, but the mechanism for homogeneous catalysts is pretty well known. I'm going to show you how this works. So again, we form an actual catalyst from a pre-catalyst. So in this case, the pre-catalyst can be a zirconium complex, a cyclopentadiene zirconium complex with an additional methyl group, an additional chloro ligand. And statistically, that complex can lose a chloro group, and then it forms this actual catalyst, which has a lower coordination number and is the actual reactive species. So now what this can do is it can add an olefin, in most simple case, an ethene molecule to the unoccupied vacant site. Okay, and that olefin can just bind side on. So now what you see here again is that you have an unsaturated molecule next to an anionic ligand, which in this case a methyl group, and that gives rise for the possibility of a migratory insertion. Okay, so through a migratory insertion, we can then produce a longer alkyl group. But as we do so, we decrease the coordination number, because of which a new ethene molecule can bind. Okay, And now again, we have the same situation. We have an olefin next to an anionic ligand. In this case, it's a propyl group. And that gives rise to the possibility of, oh, there's a question in the chat. Migratory insertion. Yeah, I'm sorry, I did not see your answer, Ruth. Very good. So this is gives you the possibility for another migratory insertion. And you see that this leads to another elongation of the alkyl group. And of course, now we can add another eth molecule, and the alkyl chain can just grow and grow and grow until we have a high molecular weight polyethyl. And of course, there are also possibilities to terminate the polymerization, detaching then the alkyl chain from the catalyst. So this is how industrially polyethylene is made from ethylene reaction, which is performed at a very large scale. Okay, another very important industrial reaction is the hydroformylation reaction. So what do we mean by hydroformylation? In a hydroformylation reaction, we start out with an alkene, and then in the presence of carbon monoxide and hydrogen, we convert our alkene into an aldehyde. And we formally add CO and dihydrogen to the alkene molecule. And of course, there are two possibilities to do this. We can attach the carbonyl group here to the terminal, to this terminal carbon. Then we get a linear aldehyde, but we can also attach it to the other end, to this carbon, and then we're getting a branched aldehyde. So these hydroformylation reactions typically produce mixtures, and the ratio of these mixtures depends on the olefin with which we start, but it also depends on the actual reaction conditions. So this reaction is catalyzed using a molecule that we've also previously encountered. It's this carbonyl hydride, HCO-CO-CO4. So now how does this reaction work mechanistically? So again, the carbonyl hydride is actually formed in situ, and it's formed in situ from hydrogen and our cobalt dicarbonyl, which we have learned previously in the chapter about carbonyl. So this exotic molecule has really large scale application. One wouldn't believe it maybe when we first see it, but it actually does. So it can react with hydrogen in a reaction which we again would be able to name. Also an example, oxidative addition. Yeah, in this case it's dinuclear oxidative addition. And this forms the carbonyl hydride in situ. And then this carbonyl hydride can statistically lose the carbonyl and add the alkene. So this is nothing else but a substitution reaction which can statistically happen. And the alkene binds side on to the cobalt. So now again, you see you have an unsaturated molecule next to an anionic ligand. And so this gives rise to a migratory insertion. So that produces you an alkyl group and a vacant site. Okay, but this vacant site can immediately be reoccupied by carbon monoxide, which is in the reaction system together with the hydrogen at high pressure. So yeah, this migratory insertion can actually happen in two ways. The hydrogen can either be located here, and well, this carbon binds to the cobalt, or the hydrogen can be located here, and the other carbon binds to the cobalt, and so you're getting a mixture of these two compounds. For that reason, you get eventually also the mixture of aldehydes. Okay, let's pursue this molecule further. Of course, that molecule could also undergo follow-up reaction. So this molecule can now undergo another migratory insertion, because our carbonyl ligand is also an unsaturated molecule, and we have now an alkyl group next to it. So we can do another migratory insertion, and the respective vacant site that we produce gets reoccupied using a carbonyl ligand. All right. So now in the next step, we can add hydrogen. So we can add hydrogen, sorry, in oxidative addition step, and we can at the same time lose a CO, and that produces then this complex here. So now this complex here can now undergo a reductive elimination, okay, which then forms the aldehyde, and at the same time reforms the catalyst. And then the catalytic cycle can begin again, and another olefin molecule is being transformed in aldehyde. So as mentioned before, this is not the only aldehyde can form, also the branched aldehyde can form. With this reactant here, which is popular in this case, you get a linear to branched ratio of 3:1, so you have to separate the mixtures afterwards. Okay, now there are variations of this hydrocarbonylation. You cannot only use the pair carbon monoxide and hydrogen, but also carbon monoxide and other molecules. So for instance, if you use water and CO, this is called a hydrocarboxylation. You can also use alcohols. This would be a method to produce esters from alkene. It's called hydrocarboxylation. It's also possible to use amines in combination with CO, and that is a synthetic route to form amides, and the respective reaction is then called a hydroamidocarbonylation. Okay, let us go to the next process, which is the Monsanto acetic acid process. So this is the industrial way to make acetic acid. And it also uses an organometallic catalyst, in this case a rhodium complex, rhodium I2CO2 minus, in conjunction with a second catalyst, which is hydrogen iodide. So we have here a cold catalytic system, which is able to react methanol with carbon monoxide to form acetic acid. Okay. So how does this work? So first of all, the methanol can react with HI to form methyl iodide. Of course, this is a chemical equilibrium. The reaction actually lies more on the side of the methanol, but we form enough methyl iodide that follow-on reaction steps can proceed at a significant rate. So now this methyl iodide reacts with our rhodium catalyst. Okay, so this is a square planar catalyst with two carbonyls here, and these two iodo groups here. Overall, this is negatively charged because it's a square planar. It should be 16 valence electron species. We count our electrons in order to verify this. But now this methyl iodide can do a reaction which could be identified as oxidative addition, correct, to form this compound here. So this, in this case, a trans addition with the methyl group and the iodo group are on the opposite side, whereby no, we could not actually really distinguish because we have here already iodo groups. So it may be cis or trans addition. But regardless, this can now undergo a follow-up reaction. We see again we have a carbonyl group, which is an unsaturated group, next to a methyl group, which is an anionic group. So that can undergo a migratory insertion. So the carbonyl group gets inserted into the bond, the methyl rhodium bond here. So now, what can happen to this species? So this species can pick up another CO because we have basically created here a vacant site and we have carbon monoxide in our system. And in the next step, we can reform the catalyst under the reductive elimination of methyl iodide. Okay, so now this acetyl iodide can react with methanol. Okay, so that gives methyl iodide and acetic acid, and that methyl iodide can then undergo further reactions with the reformed catalyst and the catalytic cycle can begin. Okay, last but not least, let's look at a reaction that we actually have not discussed that far and its applications. That's the olefin metathesis reaction. So when an olefin undergoes metathesis reaction, then that means that formally the carbon-carbon bond in the olefin gets cleaved in the middle, and the two fragments are getting recombined in basically a new way. So you see here an example for this. We have an olefin here with different substituents. Here these red ones are 1 and these blue ones are 2. So olefin metathesis with this molecule would mean that we cleave the carbon-carbon double bond in the middle and recombine the fragments in a different way. So we would form two fragments. If we react two molecules, we will produce two fragments. that contain R1, and we could recombine two of these fragments to form this new olefin. At the same time, we could also recombine two of the other type of fragment to form this molecule. Okay, so now this reaction also requires a catalyst that cleaves the carbon-carbon double bond. Okay, because there's usually no preferred way to combine the fragments that result from the carbon-carbon double bond cleavage. This is usually an equilibrium reaction. Okay, so you do not only have the forward reaction, but then of course also the products can undergo the same olefin metathesis, and you also have the backward reaction. So in order to get a reasonable yield, you therefore usually look for a way how you can drive the reaction to the right side, and there are different ways to do this, and I will show you how that works. Okay, so we said that we actually require a catalyst to perform the olefin metathesis. What catalysts do we have in hand? Actually, two types of catalysts, molybdenum catalysts and ruthenium catalysts. So this kind of catalyst is called the Schrock catalyst, named after Richard Schrock. So it has here this aryl, the characteristic component is here this aryl amido group. And there are the so-called Grubbs catalysts, named after Robert Grubbs, which are ruthenium catalysts, which are carbene catalysts. So the characteristic here is that you have a ruthenium carbon double bond. In addition, you have here chloro groups and bulky phosphates. So these ones are more reactive here, but they're also more difficult to handle. So they're very sensitive and touchy. So the Grubbs catalysts are less touchy, but also not that active. Both types of catalysts have found applications, and both Richard Schrock and Robert Grubbs have received the Nobel Prize for these catalysts in 2005, I believe. Okay, so now let's do some olefin metathesis using these catalysts. So what is the synthetic scope? So oftentimes you use olefins that have a terminal carbon-carbon double bond. And the reason for this is that you produce, in this case, ethene as the second product. And ethene is a gas, and a gas can be purged easily from the reaction system. And this is a way to drive the chemical equilibrium to the right side. Okay, just to move the ethene, the volatile component from the reaction system, driving to the right side. Okay, so another form of metathesis is the so-called acyclic diene metathesis, ADMET. That is a way to form polymers. So in this case, you have a diene with two terminal carbon-carbon double bonds. So now you can cleave this carbon-carbon bond in the middle here. You can cleave this carbon-carbon bond in the middle over there. You can combine the two CH2 groups again to make ethylene. Okay, and now the other fragment has two reactive ends. Yeah, here and here. And now you can combine these reactive ends to make a chain. Okay, and that chain then has both saturated carbons, which are these here, as well as unsaturated carbons. So you have 1, 2, 3, 4 carbon-carbon single bonds, alternated by carbon-carbon double double bond to single bonds, and then double bond to single bonds, and double bond. So this is how you can make unsaturated polymers. All right. Then another variation is ring opening metathesis polymerization, also abbreviated ROMP. In this case, you use the ring strain in an unsaturated molecule in olefin. So for instance, you can start out with norbornene, which is an alkene, which has a relatively strained ring here. And as you add the catalyst, the carbon-carbon double bond cleaves. And then, because the ring strain is relieved, the reverse reaction is suppressed. And instead, the fragments recombine the opposite way, and again, you're getting a polymer. So this is another way to make polymers which are unsaturated. In this case, we would have a cycloheptane ring in between two unsaturated carbons of the polymer. All right, so the opposite of that is called ring closing metathesis. So here you form a ring that can form easily because of kinetic and thermodynamic arguments. So this way you can especially form 5-membered rings and 6-membered rings, which are quite stable. So here's an example for this. So again, you have here a diene with terminal double bonds. So now you see that these double bonds are 1, 2, 3 atoms apart. So this means that as we cleave this carbon-carbon bond here and this carbon-carbon bond over there, we form a fragment that can very easily react intramolecularly to form an alkene, which in this case is ring alkene. So as a side product, you get again ethylene can again drive away this ethylene from the reaction mixture to drive the chemical equilibrium to the right side. All right, so finally, and that will be the last part, how does the olefin metathesis reaction work mechanistically? So it relies mechanistically on a series of reversible 2+2 cycle additions. So our catalysts are all carbene catalysts, so have a metal carbon double bond, and that metal carbon double bond can react with an olefin in a 2+2 cycloaddition reaction. So that forms a 4-membered ring here, and that 4-membered ring is strained. So it can relieve the strain either by just the reverse reaction, okay, but the ring can also open in a new way, making new bonds. So it can also cleave so that this electron pair here goes here, and this electron pair here goes over there. So that forms a new carbene, and it forms our first reaction product, which is this olefin here. Okay. So now this species here again has the capability to react with another starting molecule to form another 4-membered ring. So again, that 4-membered ring can open and now produce our second metathesis product, which is in this case acetic. And then we have reformed our original catalyst, and the catalytic cycle can begin. Okay, so this is what I wanted to tell you.